Okay, so welcome guys. So in this video, I will talk about Green's theorem. Basically the first and the two Green's theorem, and also the uniqueness of the Laplace equation. Uniqueness of Laplace equation. Okay, before I start, please subscribe to my channel. Okay, so usually I like to do this kind of short videos to just organize the idea very quickly. So I think it would be very useful if you're learning electrodynamics or the vector analysis. Okay, so let's quickly go through the theorem I want to say is that the first I will derive the Green's first and second identities. Okay, so the proof is very simple. So let's first start from the divergence theorem. Right, so we have this divergence theorem. A is a vector field, and the D3x, that will be A and dA. Okay, so I usually like to use S, right? So basically you have V, a volume, and you have surface S, right? And A is a vector field, and yeah, so this is the in R3. Okay, so the first one is if I replace A be the phi gradient psi, and I also know that the divergence of A will be grad of phi Laplace psi, and this is just a chain rule, right? So if I can plug in, then I will get the volume of this one. The volume integral, and the surface will be phi grad, right? N dA. So usually people will write this as partial phi partial n. So this is a definition of the directional derivative. Okay, so this is the first one. Let's so-called the first Green identity, which we will use quickly. Okay, and the second is that the second Green identity. So second Green identity just exchange this phi and psi. So you see when you exchange that, this term looks the same, right? So you get the psi partial phi partial n dA, and you use the first term to this equation to minus this equation. Okay, so you get our second Green's identity. So it's this one minus this one. dV will be surface phi partial phi psi partial n plus psi partial phi partial n dA. Okay. So this is the second Green's identity. Okay, and the second Green's identity have applications. So maybe I can derive it now, or maybe derive in next time. Okay, so yeah, so maybe I derive this time. So the second Green identity has a application that we can suppose that this phi, right? This phi satisfies this Laplace equation. I suppose you have a charge rho and minus 4 pi rho, and your I can choose this psi. I can choose psi. I choose psi to be like 1 over r, right? So it means that 1 over x minus x prime. Okay, I can pull in. So we get the phi, right? So phi is here, and this guy will be minus 4 pi delta x minus x prime. So it's a three-dimensional Dirac delta potential minus psi 4 pi rho dV. Right. So it will become a surface S. Phi partial n prime. Okay. Okay, I change n to n prime just to indicate that we are doing the integral on the surface. Okay, then you can combine all of it, and then you get the phi is equals to, right? But this is x prime, right? So if you do the x prime integral, you get the remaining x. So you get the phi of x. So remember that you are doing the integral on x prime. Okay, so your phi of x is this one. Alright, so this term is simple because you get the phi and you shift this term before go to the right hand side. Okay, so you get the. So this is a famous equation that usually people will use in the electrodynamics. Okay, so it's this one. So this is the surface. Okay, this is a volume. Okay. Okay, so the next thing is that we want to use the first screen identity to prove the uniqueness of Laplace equation. Okay, I think this proof is somehow really interesting. Okay. So let me just quickly write down the first screen identity. Okay, so this is surface, this is volume. Okay, so idea is that what means the uniqueness is that suppose you have a Laplace equation. Let's say your Laplace equation is this one, right? And I give you two kind of boundary conditions. One is the Dirichlet, means that the psi on the boundary is fixed. Okay, so this one, or the partial psi partial n is fixed on the surface. Okay, so you have two kind of boundary conditions. Okay, so the theory is that the solution is unique. It's unique in this V. Okay. So to prove is that the proof idea is that okay. So the proof idea is that we can just let so let's let phi equals to psi equals to. Okay, so that it's too quick. Okay, so why the solution unique, right? So proof. So suppose not. So let's suppose that we have two solutions. Okay, so let's say U2, U1 are solutions. Okay, so that means they are both the same. They are both 0, right? And they coincidence on the boundary. So I can define a so-called large psi to be U1 minus U2. Okay. And I just let psi and phi equals to U1 minus U2. Okay, so okay, I think okay. Okay, it's fine. Yeah, I just let psi and phi equals to U1 minus U2. Okay, so the notation is a little bit unclear. Okay, so now up to now we have V and psi gradient psi, right? So it's the length square dV will be surface psi partial n dA. Okay, so either side, so right, if size this one, right, either side 0 or partial n is 0. Okay, so we get 0, and both, and we also have this is 0, right? This is a definition of the Laplace equation, right? So then you will get the volume graded phi length is 0. Right, so that means graded phi is this is continuous. This is a non-negative function integral in the continuous region, right? So that means dl phi, right? It's 0. Okay, so dl phi 0 means that so by the mean value theory, right? So U1 and U2, right? It's basically connect with this dl phi, right? So basically you can view dl phi means the derivative at each directions of this size 0. So that means U1 is the same as U2. Right? Because if you start from some points, then to connect another point that there's no gradient alone, right? So that means U1 and U2 equals U1 equals to U2. So the solution is unique. Okay, so okay, so let me see what I want to talk about. Okay, so be sure to that's it, and be sure to subscribe to my channel, and I will see you guys in the next videos.